Good morning, everybody. I am Dr. Janardhanan. I'll be handling this course, which is Biofluid Mechanics for Biomedical Engineering. And the course code is BMEG 3121 and it has a credit score of 5. In fact, this course will be handled by myself as well as Mr. Kameda from our department. And the time period will be from September 2025 to January 2026. This is actually a blended course. What it means is a part of the course will be taught through online and a part will be taught through offline or conventional teaching methods. So the first 3 chapters, which deals with mostly the fluid mechanics and the theories behind fluid mechanics, will all be taught in the online mode. And mostly I'll be handling these 3 chapters, and the rest of the chapters will be handled by Mr. Kameda. I'll be referring to these standard reference books, one on fluid mechanics and the other one on biofluid mechanics. The name of the book, the author of the book is Munzen, The Fundamentals of Fluid Mechanics, and for biofluid mechanics it's written by Professor Krishnan. And this is myself and this is Mr. Kameda. And the course outline starts with the introduction of biofluid mechanics. In fact, humans were exploring this fluid mechanics for a long time, but in particular biofluid mechanics was inspired by the flow of blood in our body and what causes it to flow, all the reasonings behind it. In fact, the good book to refer for this would be Biofluid, and you can look into these chapters for more details on the history of biofluid mechanics. And then comes the nature and fluid properties and types of fluids. In fact, viscosity is a property of fluid, and the stress-strain relationships for solids as well as fluids. When we talk about fluids, it not only refers to liquid, it also refers to air, gaseous states, because they all flow. So the stress-strain relationship will differ, and based on that, we try to classify the types of fluids like Newtonian, non-Newtonian, and there's a constituency equation which relates the stress with the strain, and the more details will be taught in this chapter. And the book to refer would be Krishnan. Yeah, here we talk about the basic properties of fluids and surface tension, and viscosity, density, all these properties will fall. And this book is also good. This is by Patrick Casey, Fundamental Fluid Mechanics. Here it will be very general. It's not specifically for biofluids. It's general for all the fluids. Moving on to the next chapter, which is chapter 2. Here we talk about the differences between the fluid flows, or description I would say. For example, in solid mechanics, Lagrangian approach plays a very important role, whereas in fluid mechanics, Eulerian approach is very important. The reason is pretty obvious, because in Lagrangian approach, we follow the body whose property we are observing, whereas in Eulerian, we have a control volume, and within that volume we measure what are the properties we want to do. And there are, the classification of flow as these 2 types, was laminar and turbulent flow. These all can be derived from the Navier-Stokes equation. In fact, the transition from laminar to turbulent and Reynolds number, which is a dimensionless number, From this, these all concepts can be easily understood. And after that, we look into the flow within circular pipes, like shown here, and flow between parallel plates. It's also called as cork flow, and then flow between two concentric circular pipes. In fact, I'll be teaching this chapter after the chapter 3, because once you understand the chapter 3 with all the governing equations, it becomes easier to follow the different types of flows. And when it comes to governing equation, we have this conservation of mass, conservation of linear momentum, and finally we arrive at the Navier-Stokes equation. So the book I'll be referring to are mostly Munson. Particularly, we'll start with the derivation of Reynolds transport theorem. Reynolds transport theorem, which is mentioned in this chapter 4. So derivation of the Reynolds transport theorem is important. So once Reynolds transport theorem, we start with the Reynolds transport theorem for a control volume shown here, and then we go on to derive the continuity equation for a finite volume, which is a somewhat larger volume, for the conservation of mass, and then we also derive for the linear momentum. These two are macroscopic approach because we consider finite volume, and then we also move on to derive the differential equation for the same, for the continuity equation, and the differential form of linear momentum turns out to be the Navier-Stokes equation. So we will derive that, and once we have the linear momentum equation, okay, which is precisely given in this book by Krishna. This is a vector form of the Navier-Stokes equation, and then this is the differential form of the Navier-Stokes equation in Cartesian coordinates, and it also can be transformed to cylindrical coordinates. Once we have this, then we can go and look at this different flows like parallel plate flow, the curved flow, as well as the Poiseuille's flow. We can derive this equation pretty easily. With this, we end this theories, and then we move on to application chapter, chapter 4 and 5, which deals with the flow of blood in blood vessels, how the pressure and velocity varies inside arteries, veins, and capillaries. And also we look into the rheology, which is like the stress-strain relationship, particularly for biofluids, okay, with time, with respect to time, how these properties of blood varies. And the reference for these chapters would be this book, Jagan Mazumdar. You can look at these contents like rheology, blood rheology, circulatory biofluid mechanics, and also Krishnan also has some of the interesting topics which are required by this chapter. And I would like to add the importance of Navier-Stokes equation. These equations, though derived from linear momentum, in fact comes under broader topics called transport phenomena in chemical engineering. So we talk about mass transport, momentum transport, energy transport, species transport, and so forth, and the concerning conservation laws like mass, linear momentum, species and energy. So if you get used to this Navier-Stokes equation, you can address many modelings, not only in biofluid mechanics but also in solid mechanics, and also in optics, because light is a form of energy and heat transfer. All these things can be easily understood. So I hope you enjoy learning these interesting and advanced concepts, and which will help you in your future academic as well as research careers.